So electron configurations. In order to understand how quantum mechanics helps to explain the periodic table patterns, we need to look at how the electrons are arranged in the different elements. So quantum mechanics describes the behavior of electrons in atoms. And we've already had an introduction to quantum mechanics. The electrons exist in orbitals, which are regions of probability where it is likely that an electron will be found. We can think of them as being like orbits, but an orbit is a circular path that an electron would travel like a planet around the sun, and that's not how they actually behave. So if we describe the orbitals in an atom that have electrons in them and how many electrons are in each of them, that collection of descriptions is called an electron configuration. For something like hydrogen, which only has one electron, the electron configuration is very simple. So here we're designating this is the principal energy level 1, the S sublevel, and there's one electron in that orbital. So I talked to you about the quantum hotel. I called it the Electron Hotel. I'd forgotten. I had a better name for it. It's the Quantum Hotel, a discount resort for electrons. That's its official name. So in the Quantum Hotel, this electron configuration is like the notes that the guy at the front desk takes so that he can keep track of what rooms are full or not. And so he's saying, well, on the first floor in the S room, there's one person staying. This is the electron configuration for hydrogen. When we do calculations with Schrodinger's equation for hydrogen, we see that one electron is occupying the lowest energy orbital. We can solve Schrodinger's equation for the hydrogen atom because it's simple. It has one electron. And we did some calculations with that before spring break where we measured wavelength and looked at what transitions those electrons were making to give off that light. But when you get more than one electron, things get complicated, and we cannot actually solve Schrodinger's equation. There are no exact solutions. We can only get approximations because we have additional terms for the electrons interacting with each other. So we just get approximate solutions, but these approximate solutions do show that the orbitals are a lot like those in hydrogen. For hydrogen, we can solve them exactly, but for other elements, it's just an approximation. So there are two things that we have to consider when we have all the other elements which have more than one electron, and these are electron spin and energy splitting of the sublevels. And we'll get to that. So we talked about electron configurations. An orbital diagram is similar to an electron configuration, but it's more of a picture. Here we're using boxes to indicate the different orbitals, and we're using arrows to indicate the electrons. If we have this arrow pointing up, and it's always a half arrow pointing up, this means that this electron has positive spin. If it had negative spin, we'd draw it pointing down. So remember that spin quantum number, m sub s, the electrons can either be plus 1/2 or minus 1/2. So this is a plus 1/2. And by convention, we draw the first electron with a plus 1/2. So thinking of the quantum hotel again, we talked about the orbitals as being beds and the electrons were people, right? And there were two people in a bed. I said they were guys. Well, two guys sleeping in a bed, they don't want to sleep in the same bed. And so to avoid, anything creepy, they sleep head to toe. And so the first guy going in, he's going to sleep right side up. The second guy coming in, he's going to sleep upside down in the bed. Does that make sense? So I imagine this as being this box is the bed, and I'm drawing this electron as the guy, and the arrow here is his head. He's sleeping right side up. If we look at a group of hydrogen atoms, though, each atom has one electron in it, we see that the spin is actually fairly evenly distributed. About half of them will be plus spin and half minus spin. So the Pauli exclusion principle tells us that no two electrons in an atom can have the same 4 quantum numbers. You have a question?
I had a question for the last slide. How do we know if it's going to be negative just by itself?
Well, you can't predict whether it will be negative or positive.
What would dictate if it was going to be negative or positive?
Well, you would just have to observe the specific electron. And so what we do, just to make things simpler, what we'll find is that when you have 2 electrons in the same orbital, they will always be spin paired. One will be plus and one will be minus. So that is always the case. And so just for convention, to make things simpler, we always draw the first one as positive and the second one as negative. That's not actually how they are, but that's just how we do it by convention. Because actually it doesn't really matter if we know which one's positive and which one's negative. Does that help?
Yeah, it does.
Yeah. So we can't have 2 electrons that have the same 4 quantum numbers. So if you have 2 electrons in the same orbital, and each orbital can hold 2 electrons, 3 of their quantum numbers are going to be identical. The principal quantum number, n, they're going to be on the same level. The sublevel, quantum L, so are they in an S sublevel, a P sublevel, a D sublevel? And then M sub L is the specific orbital that they're in. Those 3 numbers are going to be the same for the 2 electrons in that one orbital. But the 4th quantum number has to be different. And so what we find is that each orbital can have a maximum of 2 electrons, and they have to have opposing spins. And so in the quantum hotel, this is the people sleeping head to toe instead of next to each other, shoulder to shoulder. When we know the number of orbitals in a sublevel, we can actually calculate how many electrons could be in that sublevel. The S sublevel only has 1 orbital, so it can only hold 2 electrons. The P sublevel, and remember this, this would be equivalent to the P room in the quantum hotel. The P room had 3 beds. So how many electrons, how many people can sleep in that room? 6, right? So the P sublevel has 3 orbitals, it can hold 6 electrons. The D sublevel has 5 orbitals, it can hold 10, and the F has 7, it can hold 14. I think it's just kind of cool that these are odd numbers, 1, 3, 5, 7, and so then these are just doubles of that. And we didn't make up this pattern. This is scientists looking into the atom and just observing. And we go into these minuscule things and we find this order. I just think that's amazing. So let's look at helium. Helium has 2 electrons. So the electrons are going to be in the lowest energy orbitals that they can be in. The people staying in the quantum hotel are going to stay in the cheapest rooms. Well, the lowest energy level is the first level, level 1. And there's only 1 sublevel there, it's S. And so both of those electrons are going to be in that 1s orbital. So in the hotel, this is equivalent of you got 2 guys staying in the hotel. They're both in that the only room on the first floor that has 1 bed. And so we draw this picture with one of them sleeping with his head on top and the other sleeping with his head on the bottom. And here's a table showing the different quantum numbers for these 2 electrons. The first 3 quantum numbers are the same, but the 4th one is different. So each electron in an atom has its own unique set of quantum numbers. Any questions?
That positive and negative, that's just for, what does that mean?
So the positive 1/2 and the minus 1/2 represents a quantity, a characteristic of electrons called spin, which is...
but it's not charged.
It's not charged. No, it's spin. And so I think the easiest way for you to think of it is to think of them like tops, perhaps, and one spinning clockwise and one spinning counterclockwise. And so, no, it's not the charge on the electrons, but one has a positive spin, one has a negative spin, and that's what allows those 2 electrons to be within that same orbital together, because otherwise we find that 2 negative charges would repel each other, right? So this is how they can manage to to be together. This is how the two men don't like to sleep in the same bed, right? Two guys that aren't interested in each other, they do not want to sleep in the same bed, but it's a rule here they have to. And so this is the only way they can manage to do it. It's like, I'm putting my head up here, and you put your head down there, and we'll just avoid any funny business, okay? Any other questions?
What if they have stinky feet?
What if they both have stinky feet? Well, then they're both motivated to wash them.
How much is the orbital?
Well, the orbitals vary in size.
Depending on the element.
Well, no, it depends more on the principal quantum number. So the 1s orbital is smaller than the 2s orbital. But the orbital itself is far larger than the electron. It's very confusing to think about. If we look at hydrogen, the sublevels in each principal energy level all have the same energy. So what the heck does that mean? It means if you go to the second energy level, principal quantum number 2, where you have an S sublevel and a P sublevel, all of those orbitals have the same energy. In the hotel, on the second floor, the S room and the P room, you would be charged the same. That's not true in multielectron atoms, which is everything but hydrogen. What we see in the more complicated atoms is that the S sublevel is a little lower in energy than the P sublevel. And the D sublevel is a little higher, and the F sublevel is a little higher. And then it gets even more mixed up because you even get some interchange between the different principal energy levels. So in the quantum hotel, I say this is like there's a Groupon deal, right? And so there's these specials on different rooms. And so it can be a little hard to figure out, but I'll show you how we can figure it out just by looking at the periodic table. If we have orbitals that have the same energy, those are called degenerate. So the 3p orbitals within that subshell are always going to be degenerate. In hydrogen, the 2s and the 2p are degenerate, but in other elements they're not. So what we see is we get this splitting of the sublevels, and that's caused by interaction of charges. It's also caused by shielding of some electrons by other electrons, and also penetration. And so in general what we see is the lower the value of L within a principal level, the lower the energy of the orbital. So generally speaking, the S sublevel is lower in energy than P, which is lower than D, which is lower than F. Any questions about that? I kind of have to tell you a bunch of junk, and then we'll have some diagrams that'll hopefully help it be a little clearer. Coulomb's law describes the interaction between charged particles. And this is a physics equation. And we're not really interested in this constant part here, but we're interested in Q1 and Q2. Those are the charges of the particles. And I just found another typo. This is Q1 and Q2, superscripts instead of subscripts. So the two charges, and then R is the distance between them. So if you have a +1 and a -1, they're going to be attracted to each other. If you have two positive charges, they're going to be repelled, and the energy will be negative. So E here is the potential energy. So if Q1 and Q2 are larger, maybe +2 and -2, the potential energy is going to be larger. And then R is the distance between them. As R increases, the potential energy decreases. And you can see this with papers and magnets on your refrigerator. You get a little cheapy magnet and you stick it in the fridge, it sticks just fine. And then you put up one piece of paper and you put the magnet on it, it's fine. But you keep adding sheets of paper, and you're going to get very quickly to a point where one more sheet of paper and the magnet doesn't stick anymore. Did you break the magnet? No, you're increasing the distance between the magnet and the refrigerator, which is what it's attracted to. As you increase that distance, the force of attraction decreases. And so this potential energy is dependent on the distance between things. And we're going to see this in looking at the force of attraction between the positive nucleus and the negative electrons. So in each multi-electron atom, we've got attraction of the electrons to the nucleus, but then we also have repulsion. So this electron's saying, I'm really attracted to that positive nucleus, but I don't like these other negative electrons. I'm repelled by them. And so there's attraction and repulsion going on. And this results in what we call shielding. I think I have a picture. Yeah, there's a picture coming up. I'll talk about it then. So the electrons, especially those that are more towards the outside of the electron, of the atom, are shielded from the nucleus. So they've got these negative electrons between them and the nucleus, and that decreases the attraction that they have for the nucleus. The amount of attraction that the electron feels is called the effective nuclear charge. And this effective nuclear charge, it's symbolized Z, F for effective, is what measures the amount of shielding. So that's the effect of decreasing the charge on the nucleus. The charge on the nucleus is the same, but because there's these other electrons between the nucleus and the electron we're looking at, the net charge on the nucleus appears lower, and so the force of attraction is less. Penetration has to do with how close the orbital is to the nucleus. The closer the electron gets to the nucleus, the stronger the attraction. But when we looked at all of those orbitals and we did all those crazy diagrams, we saw that there were nodes at the nucleus and that the electron never gets right to the nucleus. The amount of penetration, and by that we mean these larger orbitals having regions that are close to the nucleus, where they penetrate into those inner electron clouds and allow that outer electron to get closer. That the amount of penetration is related to the orbital's radial distribution function, and we'll look at a picture of that as well. So let's look at lithium. So lithium has 3 electrons and it has a +3 charge on its nucleus. So here's the +3 nucleus, and these 2 electrons are in the first energy level. They're in the 1s orbital, and so they're going to be close to the nucleus. And this electron is in the second energy level, which on average is farther away. So when this electron looks through here, and remember these electrons are really, it's more of a standing wave. It's not that they're just here and here, but really they're kind of occupying this whole space. When it looks in, we've got this +3 nucleus, and then we have these 2 negative electrons, which essentially knock off 2 of those positive charges. So this one electron looking into this cloud experiences a net charge of about +1. That's its effective nuclear charge, because these other 2 are occupying some of that charge. If the electron can penetrate into this region, now these guys are not between it and the nucleus, and it experiences the full +3 charge, and so that's going to have a higher amount of attraction. Any questions? I'm having this weird analogy here. I know some people went to Disneyland over the break. We did not, but one of the things some little children like at Disneyland, you think of the little girls and they want to go see the princess, right? And so you're attracted and you want to go see the princess, but there's this huge crowd of people around. And at least for the parents, we're like, I don't really want to stand in the line. This big crowd of people decreases the attraction you have for the princess in the middle, right? Now, if you were on some VIP tour or something, and were able to just go through the crowd and get closer to the princess, then it would be more appealing, it'd be more attractive to go and try to get her signature. Does that make sense? That's kind of what I see this like. Here, this electron has some special ticket and it can get in closer. So it's more attracted to this nucleus than it is when it's out here. We've got effective nuclear charge going on, shielding by these guys, and then we also have distance issues.
What's the ticket in that?
Well, this one having some special access would be because of the specific orbital that it's in. We'll see that the shapes of the orbitals, some of them allow the electrons to get in closer than others do. So here we have total radial probability for several different sublevels or orbitals. So here's the 1s orbital. And this one, you know, the total radial probability is really off the chart here. So this distance here tells us that the force of attraction for the electrons in this 1s orbital to the nucleus is very high. And if we look at the 2s orbital, we see that it's got this little part in here, it's got a node, and then it's got this larger lobe out here. But this part right here means that the electron in this 2s orbital can get closer than if it didn't have this bump here. Then we look at the 2p. The 2p doesn't have a node, and it just comes up and goes back down. And so the 2p orbital just doesn't penetrate as much. It doesn't get as close. Does that make sense? So an electron in this red, this 2s orbital, could be over here and be much closer to the nucleus. It's going to feel a higher amount of attraction. So that's going to be a better situation for an electron to be in. It's a lower energy situation. That means that the 2p orbital is going to be a little higher in energy than the 2s. In the hydrogen atom, this doesn't happen, and the 2s and the 2p are degenerate. They have the same energy. But because of this penetration and shielding, we see that the 2p orbital for any other element is actually a little higher in energy than the 2s. That make any sense? Smidgen, perhaps? So we see that the sublevels of each principal energy level are not degenerate. In the fourth and the fifth levels, this becomes so important that the 4s orbital is actually lower in energy than the 3d orbitals. And so that's where the best explanation is some weird Groupon deal, right? You know, you've got this weird set of things that if you do this, then it's cheaper. And then just to make things extra confusing, the relative energy ordering can actually vary from element to element. Okay, so we're just, for this class, we're kind of going to ignore that, and we're just going to pretend that they all order the same. But I do need to, you know, put that disclaimer in there, that if we come across some where the ordering's a little different, I did warn you that that could happen. Okay, so here's our picture. In the hydrogen, this 2s and these 2p orbitals would be all on the same energy. They'd all be in a line. But because of penetration and shielding and interactions, for all the other elements, the 2s is lower in energy than the 2p. So if we look at this as a diagram of the quantum hotel, we're going to see that electrons coming in are first going to fill up down here. We can even just draw them in. So the first guy's going to go in there. And the next guy's going to sleep upside down. And then they're going to go in here and here. And the next guy's going to come in here. And the next guy, is he going to sleep in the same bed with this guy, or is he going to take his own bed? He's going to take his own bed. That's, of course. And the next guy. Now the fourth guy coming into that sublevel is going to have to pair up, right? So he's probably just going to take the first one he comes to, and then the next guy, and the next guy, and this guy's like, ha, I get my own bed. Yeah, not for long, buddy. Okay, and so as we go up in energy, we're going to fill the 3s, then we're going to fill the 3p. And then here's one of those anomalies. The 4s room is cheaper than the 3d room. The 4s sublevel is lower in energy than the 3d sublevel. And we don't need to understand exactly why that is. We should have an idea. The penetration and shielding are what account for this splitting. But what we just need to remember is what the order is. And so we get the 3s, 3p, 4s, 3d, and then the 4p comes in, and then the 5s, and it gets all jimbled up, right?
So, once you fill up all three of the 3P,
Well, I can.
do you go to the 4A?
So
or do you go to
I'll just draw the arrows in here. I'd go in this order, and then these would fill, and then we'd fill this one,
Oh, okay.
and then we would go to the next and do this. And here these guys, you know, there'd be 5 guys in there before they have to pair up. But we'd fill that one up. And then we're going to go to 4p. and fill that one up. And then 5s would fill up. And then we get to the 4d. And it's all about choosing the lowest energy. And it's like, you know, boulders rolling down a hill. The boulder's going to roll down until it reaches the lowest point, right? And it's just stay down there. And everything in nature is going towards lower energy.
So do the orbitals exist if there's no electrons in them?
Yes. The orbitals do exist if there are no electrons in them. Do the rooms in a hotel exist if no one is staying in them? Yeah. They're just there waiting. They're empty. And so what can happen, now that I've completely filled this up, let's get rid of some of these guys. What can happen is if we zap this atom with some energy, we can bump one of these up to a higher orbital. And it'll stay up there for a little while, and then it'll come back down. And that's where we were getting those pretty lines of light that came out, the different colors, was from the energy being released again when they fall down. You had a question?
So if the electrons are acting as a standing wave, if they're not in that portion, is it still there?
Well, that's a good question. If the orbitals are standing waves of electrons, are they really there if there's no electron in there? It's really more of a potential space. The orbital exists in the sense that the wave function, the function is there, it's just that there's nothing actually doing the function. Yeah. So we can predict what the electron would do if it was in that higher energy state. This is the shape it would take and all of those things. But, you know, can you actually see the orbitals? No. No. Any other questions?
So it's just empty space.
It's empty space that's full of potential. There's a lot of empty space. So what I just kind of demonstrated is the Aufbau principle. Electrons are going to occupy orbitals to minimize the energy of the atom. And so they're going to fill up the lower energy orbitals before they go into higher energy orbitals. Orbitals within a same sublevel have the same energy. They are degenerate. So the 2p, there's 3 orbitals in the 2p sublevel. They have the same energy. The 5d, there's 5 d orbitals in the 5th level of the d sublevel. They all have the same. And so in the hotel, if you're in the 5d room, it doesn't matter what bed you sleep in, you're going to get charged the same. So that's what we mean by the orbitals being degenerate. This is the filling order. There's 3 ways to remember that. One is just to flat out memorize it. I don't necessarily recommend that. Another way is we'll show you this thing you can draw with arrows. Or I'm also going to show you how you can figure it out from looking at the periodic table. That's what I really recommend. Orbitals can hold no more than 2 electrons each. And the Pauli exclusion principle tells us the spins have to be opposite. And then Hund's rule is that when we're filling degenerate orbitals, the electrons fill them singly first with parallel spins. So the electrons coming into that room, they're each going to take their own bed if they can, and they're all going to sleep right side up because that's preferable. And so when we draw these diagrams and things, we put the electrons in with a positive spin, and then when the second electron comes in, we give that the negative spin, and they're paired up. So this is one way to remember the order of filling. So if this makes sense to you, just practice drawing it out, and then when you get your exam, not this coming up exam, but the next one, you can draw this on the back of it and write it all out. You've brought it in your head. That's not cheating. So 1s, 2s, 2p, 3s, 3p, 3d, etc. And then to determine the filling, we're going to just draw lines. So the 1s fills first, and then 2s, and then 2p and 3s. 3p and 4s. 3d, 4p, 5s. You get the idea?